thanks again to our speakers. We're going to continue to our third speaker, second talk. We are happy to welcome Yuval Hart. Dr. Hart is a faculty member at the psychology department of the Hebrew University of Jerusalem in Israel, and a fellow in the Federman Center for the Study of Personality and the Center for Interdisciplinary Data Science Center, CIDR. He has background in physics, systems biology, and mathematical models of cognition. And today his research focuses on finding mechanisms and computational principles of cognitive processes in diverse areas such as social cognition, creativity, geometric and physical intuitions, and typical and atypical behavior in health and disease, such as autism and Alzheimer's disease. Today, Dr. Hart will be presenting his work on social prediction and decision-making. Dr. Hart, thank you for joining us today. The stage is yours.
Thank you, Tasha. And actually, I have many questions for Gaurav and Patrick, but I will save them after my talk because I think there are a lot of relations between the two. So I'd be highly interested to hear what you think. Okay, so I'll start sharing the screen. Everybody sees the screen? Okay, so just thank you, Tesh, for the wonderful introduction. Just to say that generally in my lab, if I need to sort of capture what it is that we do, is sort of saying that we want to understand the basic, the fundamental building blocks of human cognition. So if just a minute, yes. So if this is Einstein, and he is built from Lego blocks, I want to understand how his mind operates. And I think it's just like Gaurav and Patrick said, it's a bidirectional thing. So if you know what are the building blocks, the computational building blocks, maybe you can try and simulate and build something which is closer to the human behavior. And I think there are many fascinating connections there. And in terms of social interactions, which is for me, social cognition is a fascinating field because people are sort of, at the one hand, it's super complex problems, right? These are things that even current machine learning algorithm with all its might and glory, it has difficulties approaching. So it's a big challenge. And on the other hand, people are super good at it, right? So both in collaboration and competition scenarios like here and medical settings and also romantic dating is another thing that I currently study together with Shira Tzil, who gave a lecture, I think, half a year ago or something like that. So want to understand the social interaction, social cognitions from body motion. And specifically in this talk, I will talk about how do we infer the intentions of others. It's a joint work with Dr. Mariam Bazili-Pashkam, currently at NIMH, and Professor Mahadevan from Harvard University. Okay, so why intention inference is so important? So I'll give you two examples. One of which is from a mythical football or soccer game. I'm not sure what's the current phrase in Japan and Australia, but the thing with the ball, and this is the quarterfinal of the World Cup at 2012. This is the legendary Pirlo going to kick the penalty kick. The game ended with a draw, and Italy is actually currently behind. So Pirlo is going to kick the ball. This is called the panekake kick. You just kick this super slow ball to the middle. And then we have some misses from England. And now the goalkeeper of Italy, Buffon, a legendary goalkeeper, still playing at the age of 40. He's that good. And this is one of the key moments. So Buffon stops the penalty kick, and Italy goes to win the game. And if you want to know what happiness looks like, this is it. Okay, so this is one example. The next example is from another kind of sport, basketball. And this is called an ankle breaker. In ankle breaker, what happens is that the attacker suddenly changes, so he goes to one direction and then suddenly changes to another direction. He does a crossover. The mind of the defender understands that and says, okay, we need to go to the other direction, but the body is not there. The body still wants to go to the right. And then what happens? People fall. Okay, so here's one example. A change, and then people fall. And this is considered one of the most humiliating thing one basketball player can do to another. Okay, so we can say that the intention inference, in a way, can sort of get you across between being a national hero, like Buffon, or the mockery of all your colleagues, like in the ankle breaker. So it is important socially. Okay, so we wanted to sort of recapture this kind of intention inference and try to tap into the cognitive mechanisms that drive them. So we did, this is an experiment Mariam did, a beautiful one. You have two participants sitting one across another with a persiflex glass here. And what they do is they need to move either to the right or to the left. They have headphones on their ears, and they get a cue, like go right, go left. And they need to get there as fast as they can. The assignment, the task of the goalie is to try and reach the same place as fast as she can as well. Okay, so 14 pairs, each one 5 to 7 sessions, each block of trials, 30 trials of right, left, right, left. We have 8 sensors, 7 sensors on the body of the attacker, and 1 sensor, just the finger on the blocker. And we measure the reactions in 240 hertz, okay, 240 hertz per second. Okay, and what we see is that when the attacker's finger starts to move, already 120 milliseconds after the finger started to move, the blocker starts to move as well, which is super, super fast, okay? If you just show people like a dot moving on the screen, it takes them 300 milliseconds. So between 2 to 3 times faster than what happens if you don't, if you just see the motion starting. So there's something happening before the motion starts, right? Another thing Mariam was interested in is trying to infer where is this signal, where does this signal come from? So she took videos of herself going right and left, and let the participants try to block. And what you see is that if you see the entire body, you have a faster reaction. If you don't see the face at all, just the finger and upper body, the torso, still you react faster. If you don't see the finger, still you react faster. If you see only the upper body, but she has sunglasses, so you can't see where she's looking, still you react faster, okay? So really you need to cover everything in order for people not to be, not to react as fast as they can. And another interesting thing Mariam did, which is quite, I found it quite clever, is taking the videos and taking all the frames before motion onset and replacing it with the frame, the first frame of a still image. Okay, so generally it's the same, right? Because there's no movement there. But having all the frames replaced by this frozen still image really changes the reaction time. Okay, so people utilize some kind of information even before motion starts, and what we wanted to understand is what kind of information might be there. And the previous talk is an excellent introduction also to mine, because what we thought is that this kind of change between still static motion and starting to move is a kind of a bifurcation effect. And what we know from physical systems is that bifurcation events, these changes of the system's sort of topology, is usually accompanied with early warning signals. And I'll give you an example, which I think, Patrick, you already alluded to, this great experiment by Kelso and colleagues with synchronizing two fingers. So those of you who are not well versed with bifurcation events, so you can try the following experiment. Take two fingers. I'm guessing test sheets you and me, but let's see. So two fingers, and let's try to do it in phase. So move them together, and then faster, 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 faster. Everything is fine, right? Okay, cool. Let's do now another experiment. We'll have the two fingers out of phase. Okay, and now let's start moving them together. Faster, 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 faster. So at one point you'll see that your fingers are actually synced. Okay, so there was a phase transition. You switch from being out of phase to being in phase. And the way to understand it is that what happens is exactly like this is from the original paper at Kelso 87. So usually in physics, what we'll do is we'll describe the system as like a potential landscape. Whenever you have some kind of a well, this is a stable state for the system. So at the beginning, we have two stable states. We have the in phase, okay, 0 degrees difference between the two, and we have the out of phase stable state, which is this one. As we increase the frequency of movement of our fingers, this well at out of phase becomes more and more shallow. Okay, and at one point the well is erased, and the ball, like the system, has no option but sort of going to the stable state, which is at 0, at in phase. Sorry. Okay, but actually the cool thing is that before the well is erased, when it is super shallow, okay, the system still has this stable state. Okay, but now it is super shallow. So when it's shallow, the ball, you can imagine when the dip is super deep. Okay, when the well is super deep, the ball does these really fast movements inside. So you measure the velocity of the ball once, it's going to the right. The next time it can be to the right, it can be to the left, because the movement is so fast. When the well becomes shallower, this ball is going to move. So you measure the velocity once, it's going to point to the right. Next time you're going to measure again, it's still going to be to the right. So there is a rise in the autocorrelation. So there is a correlation between every consecutive two measurements. Okay, so this is what we call early warning signals. There's a nice review on it in Nature by Schaeffer et al. And actually, Kelso wrote another really interesting paper 2010 on the brain aspects of these kinds of bifurcations. So back to our experiment. So what we do, we have these 7 7 sensors on the finger, on the wrist, on the elbow, right and left shoulder, torso, and head. Okay, and we look on all the sensors besides the finger. Okay, besides the moving part, we're going to check all the rest. And what we see is that indeed these early warning signals. I wrote down the major two of them. One of them is the autocorrelation at lag -1, and the other one is the decay time of the autocorrelation. Okay, and both of them show these really strong spikes even before motion onset. So motion onset is around 0.4. Okay, but still you can see that well before the motion onset, you get these early warning signals in the fluctuations of the motion. I remind you that the attacker still did not move. Their finger is still on this pillow, so cushion, yeah. So you can say, okay, you have these early warning signals, but they are not indicative of the attacker's motion onset. So we tried to look at that. It looks like a lot of points, but 90% of the points are here on this time. Okay, so there is a really strong correlation, like p-value 10 to the minus ridiculous something, which says that actually these early warning signals, for example, the autocorrelation decay time, precede the attacker's motion onset by around 130 milliseconds. Okay, and if you don't have like if you look on the finger motion, which does not show this kind of early warning signals, then if you look for the early warning signal, the correlation time or the autocorrelation at lag -1, you see that there is no correlation at all. Okay, so so you can say, okay, okay, I agree. The attacker has some kind of early warning signals. How do you know that the blocker is responding to this kind of signal and not something else? So we can see when motion started with the blocker, and we see the same. It's a bit wider, but the same sort of correlation, and it's 300 milliseconds before. So the early warning signals 300 milliseconds before motion onset for the blockers with again really high correlation. Another cool thing that you can do, different kind of bifurcation events, different kind of critical transitions between one behavior to another behavior are accompanied by a divergence in the variance. Okay, so the variance really grows near the point of transition, and you can quantify it. So this is what we did in the case of a fold transition type or a sudden node bifurcation. The exponent should be around -half. In the hop bifurcation, it's -1, for example. So and you can see that indeed the distribution of the fitting power law is centered around -half. Okay, so we now know which type of critical transition. So we have early warning signals. We have the type of critical transition. So we can write the model on how people sort of make this decision. The cool thing is that the minute you have a model, you can do something nice, which is usually when I started presenting this work, so people would tell me, okay, but probably it's something in the shoulders, it's something in the eyes. Okay, like okay, all your work sort of, but I believe it's the eyes. Like the soul is in the eyes, so probably also the movement is in the eyes. So what we did is do the following. We took a dot on a screen, okay, and this dot has some fluctuations in it. The fluctuations can be either Gaussian, so there's no information in there, and they can be a correlated noise, which comes from the fold transition type of behavior. Okay, so one of them, and the dot goes right or to the left. Okay, either by default transition or just a Heaviside function, just choose randomly right or left with some Gaussian noise. And we ask people again to do this blocking. So try to figure out the second you know where to go, try to block the dot. And what we see is that people react 100 milliseconds faster to the fault transition, to the early so the dot with the early warning signals also provided a good indication for people to react faster. So this is it. So hopefully I showed you that the attacker's decision to move has some kind of early warning signals to it. The blockers probably respond to it, and the type of critical transition is a fault transition type, and people react to these kinds of transition faster than just things without correlated noise in them. So this was about the prediction. In the lab, we do other stuff like invariant sensing and robust mechanisms, and trying to figure out trade-offs between different kinds of tasks in typical and atypical behavior, and some kind of creativity, which falls under invariant sensing. Yeah, I see I'm out of time, so that's it. And whoever is interested, you are welcome to write me.